Okay, so Cauchy-Riemann equations in analytic and harmonic functions. So what are the Cauchy-Riemann equations? So we have a complex function and a derivative defined in some domain of the complex plane. The Cauchy-Riemann equations are these: ux equals vy and uy equals vx. The subscripts u sub x is the partial derivative of u with respect to x. U sub y is the partial derivative of u with respect to y. So the basic idea that we want to show is that the Cauchy-Riemann equations hold if and only if the complex function is a complex derivative. And of course, there are conditions about existence and continuity that have to be included. So we'll split this into two pieces. Complex derivative implies the Cauchy-Riemann equations, and Cauchy-Riemann equations imply complex derivative. So this is the theorem. If we have a complex function, f u of xy plus I v of xy, u is the real part, v is the imaginary part, and it's a complex function, means its domain is somewhere in the complex numbers, and it maps complex numbers to complex numbers. And we're assuming that there is a derivative at a particular point, z0 equal to x0 plus iy0. And then we should have these kinds of things holding, right? All the partial derivatives should exist, and in fact, ux equals vy and uy equals minus vx. These are our Cauchy-Riemann equations. This is the first big theorem that we've seen, so I'm going to walk through a little bit about how to think about proving theorems. There's really here there's going to be two parts. One is exploration, and then the next part is the proof, and then what I call an elevator statement. And so we'll try and figure out all that out as we go through. So we have a complex function. We know the derivative exists somewhere. So exploration is, how do we connect these ideas to these ideas, right? Somehow if these are true, these have to be true, but how would that work? So you just think about what it is that you know. You've got a complex function and you've got some point z0, and the derivative is somewhere in the complex plane, and the derivative exists. And you know what it means for a derivative to exist? It means that this limit exists. That's really about all you have to go on, except that f has a real part and an imaginary part. And it's got an imaginary part. And what we want to show is something about the derivatives of the real and the imaginary parts. So what we can know is that u sub x, for example, is the limit as h goes to 0 of u of x plus h comma y minus u of x comma y all over h. And all these x zeros and y zeros, x's should have zeros on them, x0, y0. So what this means is that if we vary h a little bit, right, in the x0, if we vary the x coordinate but keep the y coordinate fixed, that's what ux is. So what's the difference between this kind of a derivative and this kind of derivative? For f prime of z, that's saying no matter how I go towards z naught, this limit will exist. U sub x is saying z naught is in the middle there. If I approach only this way, right, that's the only limit I need to exist. And u sub y, similarly, is limit as h goes to 0 of u of x0 comma y0 plus h minus u of x0 comma y0 all over h, right? And so u sub y is, you're only looking vertically. So u sub x and u sub y, we're really just showing that if I can do the limit in these particular directions, then that should work out. This is actually a stronger condition, right? f prime of z, that limit exists means no matter how you approach z naught, you get a derivative. This is saying if you approach it this way or this way, you get a particular limit. So can we connect these things? Well, we can, right? We can think of f of z0 plus h minus f of z0 as being u of x0 plus, we're going to have to take h here to be something, so we'll just call it a plus ib. x0 plus a, y0 plus b, minus u of x0, y0, minus iv of x0, y0, all over a plus ib, right? And so f of z0 plus h, this limit, which we know, oh, this should be over h. This expression, right? And we know the limit as h goes to 0 exists. Well, if I hold the b equal to 0, right? That goes away, and that goes away. And then this is just going to be ux plus I Vx. That's the limit that we're going to get because we can just approach it from the right and the left. But then what we know is that the limit, so this would be, if we take b equal to 0, this would be x0 plus a minus ux0 comma y0 over a plus I v x0 plus a y0, there should be a y0 over here, minus v x0 y0 all over a, right? And so then we can get, this is my ux. If I let a go to 0, this will become u sub x. And if I let a go to 0 here, I get I v sub x. So we know these limits exist because this limit exists. And we also know from what we saw before that if this limit exists, then the partials have to, not the partials, then the limit of the component functions have to exist, right? So if f of z equals u plus iv, and f of z converges to w0 equal to, we'll call it w1 plus I w2, then u is going to have to converge to that, and v will have to converge to that. So the real and imaginary parts have to converge if the limit converges. So that means this thing has to converge to something, and that thing has to converge to something. And that gives me, right, u sub x setting b equal to 0 means we're just looking horizontally. So what we've got out of this exploration is f prime of z0 is a stronger condition than the existence of these two. If I want to show that u of x exists, I just have to show that I can approach z0 along the horizontal. And I know that that limit has to exist because this limit has to exist. So this limit and this limit, which is ux and vx, those both have to exist, right? And then I can do the same thing going vertically, and hopefully my Cauchy-Riemann equations will drop out of that. So what does our proof actually say? So we needed a couple things there. We needed to know what a definition of a partial derivative is, and we needed to know this part, which I think we stated earlier in the class, but I don't know if I actually proved it. So when you're trying to prove something, right, this is one of the ways to do some kind of exploration. Think about what it is that you know about knowing that the derivative exists. F prime of z0 exists means really only one thing. This limit exists, but the limit exists no matter how you approach z0. Partials exist means that these kinds of limits, these other limits, have to exist. but those are only along the vertical or the horizontal. Since f prime of z0 exists, that means no matter how you get to z0, including along the horizontal or the vertical, has to exist. And so your ux and your uy should exist. So here's the actual proof. So gamma 1 of t equals x0 plus t plus iy0. So what does that mean? We've got a point z0, that's where our derivative exists. Gamma 1 of t is going through there. It's actually going this way, right? But we're changing t in the y direction, right? In the x direction, right? So we are fixing my y0, but we're going horizontally. So f prime of z0 is f of gamma 1 of t minus f of z0 over gamma 1 of t minus z0. This is one way to approach the origin, and so we know that, not the origin, one way to approach z0, we know that exists, so we know that this exists, so we know that exists, and so these both exist, and so f prime of z0 can be written like this. And in particular, ux and vx exist. Same kind of thing with gamma 2 of t, exactly the same argument gets you this, except now notice that we've got an it in the denominator here. Here we had a t, right? So if we're going vertically, right, this is x0 plus I gamma 0, iy0 plus it, right, if we expand that out. So this minus the point that we're approaching is actually going to give you an it in the bottom there. That 1 over I will factor out. We get the same sort of thing here. We've got a ux, a uy term here, and a vy term here. And I should have an I out here. I think I forgot. Right, because I've got an I here and an I here. And so what do we end up with? Well, the 1 over I becomes a minus I on the use of y, plus I times 1 over I just means I have a 1 times the vy. So I've got now two expressions for f prime of z0. F prime of z0 is equal to this. F prime of z0 is also equal to this. So they must be equal to each other. But then the real parts and the imaginary parts have to be the same. So ux equals vy and vx equals minus iuy. And so that's essentially the proof. Right? It's not a terrible proof, but it's one typical way how limits go. And the nice thing about this particular proof is that you know that the limit exists because it says so right out the bat. So what's the elevator statement? An elevator statement is a short statement that you could make, the idea being like, you know, you're in an elevator, you're going up 2 floors, one of your classmates or one of your colleagues says, how does this proof work? And you just want to give them a short statement and say, and they're smart and they've seen it before, they know how it works. You just want to give them a statement that gives them enough to reconstruct it without them having to look up a huge amount of details. So if you know a function has a complex derivative point, then we know that the definition of the derivative will give you the same answer regardless of which path you take to the point. So approach along vertical and horizontal lines. Since the complex limit exists, the components limits exist, and so the Cauchy Riemann equations just sort of drop out of evaluating limits, right? So the key point here is evaluating vertically and horizontally. I'm not going to go through that procedure for the Cauchy Riemann equations in full detail, but I will do a bit of an exploration. So what we've got here is a more complicated statement, and that we're saying that my function is defined not just at a point, z0, but an entire ball of radius epsilon centered at z0. In this region, ux, uy, all the partials exist and are continuous at the point x0, y0, and the Cauchy Riemann equations hold. and then the limit exists. So to prove that the limit exists, and why does this sort of have more hypotheses than the other one? So there's a limit. What's involved in showing that this limit exists? No matter what path you take, you get the same limit, right? So if we're going to actually approach like this, approach like that, however it is that we approach z0, we need this limit to exist. So why do we need all these conditions? Well, in particular, when we're thinking about partial derivatives, right? Partial derivative with respect to x is horizontal. Partial derivative with respect to y is vertical. So if I'm approaching z0 in a way that combines vertical and horizontal, right, I need to make sure that I can go this, well, you know, when I'm going this way, I need to have a partial derivative there. I need to have partial derivatives of ux and uv, partial derivatives of u and v existing here, and existing here, and existing here, right? Because I'm not just going this vertical. So at every point in here, I need to know that I actually have a derivative so that I can actually know that this thing is defined no matter which direction I come in. So I need to have them defined in there and they existed in there. We need the continuous at this point because continuity says that, well, ux at a point near, I'm not going to write it out, but that ux at a point near x0, y0 isn't going to make any jumps, right? And then these are the Cauchy-Riemann equations. And that gives us that this holds. So it has to be stronger here because we want you have to be able to approach the, how do I say this? Being able to approach the z0 in any way you want, your partial derivatives have to exist all the way along this path, and they have to exist in every path you take. So you need to have them existing in a little ball here around your original point. And so we get slightly stronger conditions. You just need that the partial derivatives exist and are continuous, which is generally not a problem. So basically, Cauchy-Riemann equations apply complex derivative and vice versa. And there's I might do a video with a proof of that at some point, but I might not. Okay, so those are the Cauchy-Riemann equations. So let a function from the complex plane to a complex plane be a function of a complex variable z, define an open set S. Why do we want to have an open set S? Well, we want to have derivatives. And what do derivatives need? Derivative needs a space around the point so that you can approach the point in every direction. And that's, you know, what it means to be open, right? Is that there's a little ball around that particular point, disk around that particular point. So, right, every point in the set has to be surrounded by a neighborhood that is entirely contained in there, so we can do the limits. So analytic, sometimes called holomorphic, means that the derivative exists at every point. The function is called entire if it's analytic on the entire plane. If it's analytic on a deleted neighborhood of a point z0, but not defined at z0 itself, then 1 over z0 is an isolated singularity. As an example of this, 1 over z, for example, is not defined at 0, but is defined everywhere else. So I should have actually an empty hole there. But it's defined everywhere else. So 0 is called an isolated singularity because there's no other singularities nearby. All the differentiation rules you know, product, quotient, sum, difference, chain rule, multiplication by a constant, these all carry over from calculus. And a standard theorem from calculus that carries over to complex analysis is the following. If a function is zero in a domain, then the function is constant. If the derivative of a function is zero in a domain, then the f of z is constant on the domain. And remember that a domain is a non-empty, open, connected set, and all of those three things are important. And so this theorem can be restated if the following things hold. It's analytic, which means it's got a derivative. The domain of the function is a complex domain set, non-empty, open, and connected. And for every point in D, the derivative is equal to 0. Then for some constant, and for every z in D, f of z equals c. So the function is a constant. And what's the sketch of the proof here? F of z equals u plus iv, and f prime of z equals 0. That means all the derivatives are equal to 0, all these partials. And then you can rely on vector calculus, and that tells you that if these derivatives are all 0, then u and v have to be 0. One thing to keep in mind here, though, is that you actually need the domain to be connected. The limits involved using derivatives require that the function is defined on this neighborhood, that the function is equal to the same constant of each of these neighborhoods requires that we can string them together like pearls on a string. And I'm not going to do the proof here because the proof is actually a notational grind, but the basic idea is if I've got this point, here's my domain, and I can show around this point that the derivative is 0, and because this derivative is 0, then these things all have to be constants. Why do I know that over at this point, where I can show all the same things, the function has to be equal to the same constant? Well, that's because I can find points, find a little path that connects the two, and then show on overlapping disks. If two disks overlap, the constant on both of them have to be the same, but I can chain these things together and show that these two can actually be the same. And so if the domain was not connected, I had another piece of it out here, and I can show that all this stuff holds, except it's not connected, well, then there's no way to draw a path to get out here. And so the function could have a different constant on this chunk than it does on that chunk. If you go back and look carefully at the statement of the mean value theorem in calculus or the extreme value theorem in calculus, they both require that you have an interval a comma b, right? And that's a connected interval. So these theorems rest on the extreme value theorem, actually. But we can't get two useful results. So suppose f of z and f prime of z are both analytic under the domain. Why does that force the function to be constant? Okay, so why does this have to be constant? Well, the sketch of the proof is, and it's actually pretty close to being a proof, f being analytic means two things. One, f should be equal to u plus iv, and the Cauchy-Riemann equations hold. F bar being analytic means that f bar, well, it's the complex conjugate of f, so it's u minus iv. But then what's the Cauchy-Riemann equations for this analytic function? Well, that'd be ux equals minus vy, because there's a minus on the v there, and then uy equals plus vx. But if we look at these two, that tells me that ux equals vy, ux equals minus vy, 2ux equals 0, so ux equals 0. So ux equals 0. Likewise, uy, vx, vy, these are all equal to 0. Right? If ux equals 0, then vy has to be 0. So all the partials are 0. So that means f prime of z equals 0. So if we're analytic on a domain and f bar are both analytic, the derivative of the function equals 0. So that tells me that the function is equal to 0. No, it doesn't tell me that the function is equal to 0. It tells me the function is equal to a constant on that domain. So that's useful. Another corollary, constant modulus on a domain. I forgot to type in the actual statement of this. Constant modulus on a domain means the function is constant on the domain. So f is from D to C. D is a domain. And what does that mean? Not empty, open, and connected. Constant modulus means the modulus of f equals a constant. So what does that mean for why the function should be constant on the domain? If the norm, if the modulus is constant, well, we know that f times f bar equals the modulus squared. That's the definition of it. So f bar equals the modulus of f squared over f. Is f bar analytic? Well, there's two cases here. If the modulus of f equals 0, then f equals 0. F is just a function that maps everything to 0. Second case, if modulus of f equals some constant, then we know that f is never 0 because the modulus of 0 is 0. So f is never equal to 0. So that means I can divide. So f bar equals modulus of f squared over f is in fact an analytic function. So then we have f is analytic. Oh, I needed to have f is analytic up here. F is analytic, f bar is analytic, so by the previous corollary, f of z equals a constant. So and all these rely pretty much just on the Cauchy-Riemann equations, and we get some interesting things here. So harmonic functions, what we've seen in our mapping examples, the level codes of real and imaginary parts are perpendicular. These Cauchy-Riemann equations show that this is true in general, and to answer the question, which sorts of functions can be the real or imaginary part of an analytic function? So you can see in this corollary and in this corollary that not all functions on the plane can be parts of a can't be parts of an analytic function, right? If f and f bar are both parts of an analytic function, then f plus f bar is 2u, and that should also be an analytic function, but it's not, it's just strictly real. So you can't just throw any function out that you want to be part of a imaginary, to be part of an analytic function. So a harmonic function is a special kind of function, uxx plus uyy equals 0. Just going to check on this. So if f of z is analytic, then what do we have? Then we have the Cauchy-Riemann equations. Ux equals vy, uy equals minus vx. So what is uxx equal to? Right? So this is the second derivative with respect to x, right? And the second derivative with respect to x is the first derivative with respect to x, and then the derivative of that with respect to x. But we know by the Cauchy-Riemann equations that the first one is vy. And so we can write this as a mixed differential, mixed partial. But we know that mixed partials are equal to each other, so we get Vxy, and then this becomes Vx respect to y. But Vx is equal to minus Uy. So Uxx plus Uyy equals 0. So if we have an analytic function, then its real part and its imaginary part are both what we call harmonic functions. To rewrite this in notation that might be more familiar if you're not used to the xy subscript for partial derivatives, we're taking this, and this step is saying that that's the derivative of, and it's the derivative, the second derivative is the derivative of the first derivative, but du dx is Vy. And usually partials like that, we would just write like this, dv. So that's, oh, I got them backwards already. So dy, no, that's right, it's dx dy. And then that is, let me undo some of that messiness. Dx dy, but this is d by dy of dv dx, because mixed partials are equal. I can differentiate with respect to y first, and then with x with respect to x first, and with respect to y. But derivative of v with respect to x is minus the derivative of u with respect to y, which becomes minus second derivative of u with respect to y squared. And then if you, so this is equal to this, and so the sum is actually equal to 0. Okay. So the other way around is also true, although we won't prove it. If u is harmonic, then there is an analytic function, f of z, with f of z equals u plus iv, and the function v is called the harmonic conjugate of u, and you can sometimes find v from u. So suppose we have u is this thing. Show that u is harmonic, find its harmonic conjugate, and what's the function that we're dealing with. So to show that it's harmonic, we need to find u sub x. That's 3x squared minus 3y squared. And then the second derivative of x is 6x. Because we're differentiating with respect to x, we're just thinking of the y's as being constants. Uy, now we're differentiating with respect to y, so hold the x as constant. Derivative of x cubed will be 0. We get a minus 6xy. And derivative of 1y with respect to y is 1. And so the second derivative with respect to y is minus 6x. And what do we find? Uxx plus uyy equals 0. It's a harmonic function. Check. What's its harmonic conjugate? Well, here's where our Cauchy-Riemann equations come in. So we'll start with u sub x equal to 3x squared minus 3y squared. But from the Cauchy-Riemann equations, we know ux is equal to v sub y, right? So whatever our function v is, and we don't know what v is, we're trying to find it, that's our harmonic conjugate. We know its derivative with respect to y is that. So what is v equal to? Well, integrate with respect to y. And when you integrate with respect to y, you think of your x's as being constant. So what's v? This is a constant, so it's 3x squared y. This is a y squared. Integral of y squared is y cubed over 3. And so we get a minus y cubed plus some function of x, which we do not know, right? So that's what v has to be. It has to be this thing plus some function of x, but we don't know what the function of x is. Why a function of x? Well, all we knew here was that the derivative of y is this. If I differentiate this with respect to y, right, you'll get 3x squared minus 3y squared plus 0. There's no y's here. It's just a function of x. So this is the correct form for v, but we need to find out what is f of x. And the other Cauchy-Riemann equation is uy equals minus vx. Or in this case, we want to do that. Because we can find vx now. Vx is differentiate this thing. So 6xy, derivative of y cubed with respect to x is 0, plus the derivative of my function f. And this has to be equal to minus uy. Well, we know what uy is. That's this up here. So 6xy plus f prime of x has to be equal to 6xy minus 1. Remember, this is a minus sign here, so we have to multiply my uy by minus 1. These go away. My f prime of x is minus 1. And I know then that f of x is minus x plus a constant. So what is v at the end of the road? Right? And there's f of x, and that gets put in here. So that gives me v. X is x cubed minus 3xy squared plus y. So what is my function? F of z, my real part is x cubed minus 3xy squared plus y. I hope I got that right. Minus 3xy squared plus y, xy squared. So we'll scribble that out and put the square there. Plus I 3x squared y minus y cubed minus x plus c. And there is our function. Can you figure out exactly what that function is? You can. It's tedious. Keep in mind that z equals u plus iv, z bar, oh, sorry about that. Z equals x plus iy. Your basic idea, z bar equals x minus iy. So z plus z bar, if you add those together, that's 2x. Z minus z bar, if you subtract them, you get a 2iy. Right? So x is z plus z bar over 2. Y is, I don't know why there's an extra bar over that z. Z minus z bar over 2i. Plug these in for x and y up here. All the z bars should drop out and leave you with z's. And that's tedious, so I'm not going to do it. So what is the point of harmonic functions, right? So harmonic functions are, if you have the steady state temperature equation, right, solutions to that are harmonic functions, right? So if I have a plate, here's a plate. I stole this from Wolfram Alpha, I think. Temperature, hot here, cold here. So temperature is flowing this way. And the lines there that you see are lines of constant temperature, right? So the temperature is the same all the way along this line. These are perpendicular, right? Your flow lines and your potentials always meet at right angles. So we know that the potential, right, the level curves of temperature are going to be harmonic. Level curves are U equals C, right? So this is U equals, I don't know, C1. Well, this is your temperature function, which is a harmonic function. The direction of flow is from hot to cold in the negative of the gradient, but the gradient is perpendicular to the level curve, so the streamlines of the flow are perpendicular to the temperature level curves. But what we know is that level curves of U, actually you'll show this in the homework, it's not very hard, are perpendicular to level curves of V. So if these temperature lines are the level curves of temperature, then the flow lines are the level curves of its complex conjugate, harmonic conjugate. So if you want to find the flow in a plate like this, if you can find an expression for the level curves of U, right? If you can figure out what U is, what the temperature is, then you can find the harmonic conjugate V, and that will give you what the flow lines are, where the temperature is flowing. And so then you don't actually have to solve any differential equations to do that. It's generally hard though, because you have to figure out what U is first. And if you can figure out where U is, you can probably figure out what V is sort of the same way. But that's one of these applications of complex analysis. If you look at the temperature in a plate like this, the level curves of temperature are harmonic functions, so the flow lines are the harmonic conjugate. And I think that's it for that.